Hi everyone. Can you hear me?
Yep.
Okay, great.
Hello, thank you.
Yes. Hi, Doctor.
Okay,
Hi,
let's wait
Kathy.
for a few more minutes until 8:05. Then we can start. Okay, I think it's time to start our lecture. So welcome you all to this machine learning subject. And my name is Choujie Zheng, and I will be your lecturer. And I will also be tutoring the Friday lab session. So I will be with you all this semester. And now let's begin. Here is our teaching team. So the subject coordinator is Dr. Peng Cheng. Here's his email, and I'm your lecturer and tutor, and this is my email address. If you have any concern or problems, or if you have any questions regarding uh, this subject's contents, feel free to contact me through this uh, through this through this email. And if you have any concern about the like admin related stuff, you can contact the subject coordinator. And here is our the structure of these subjects. And we have lecture and lab session. The lecture session is on Wednesday, and lab session is on Friday night. And in the lecture, we are going to talk about some theoretical concept about both conventional machine learning models and also the modern deep learning models that is more related to neural networks. And during the lab session, we are going to have some hand-on practice for how to implement these models and also how to apply these models to solve some tasks. And we are going to play with some data and model as well. So this subjects is divided into, let's say, two phases. So in the first 3 weeks, we are going to talk about some conventional machine learning models like linear regression, support vector machines, and some supervised learning models like k-means models. So we're going to talk about the conventional models and also commonly uh, the common machine learning tasks that we are going to solve in this field. And in the last 3 weeks, we are going to learn about the modern model structures, that is deep learning models and neural networks. So we're going to learn models that is suitable for computer vision, that is CNN models, convolutional neural networks, and also the recurrent neural networks and LSTM models that is suitable for sequential data like time series data um, and language and neural language processing. Okay, that is basically the structure for this course. And all the subject materials and announcement will be made on our LMS. So it will include the lecture notes, lab instructions, and the lab notebooks that will contain the code you are going to use during the lab session, and also other announcement about the weekly contents, and also some maybe notification about the deadline for the assessment, something like that. So you can find all this information on the LMS. So I would recommend you check the LMS subject page as often as possible. Here are some recommended readings. So there are 2 books, Neural Networks and Deep Learning, Neural Networks and Learning Machines. So these are some add-on reading materials. Those are optional. So for the assessment for these subjects, you don't need to do this optional add-on readings. If you just follow the lecture and lab practice, it will be enough to get a good score for your assessment. And this CSS 229 machine learning course that is from Stanford. It is an open course. It is a good supplementary materials if you want to know more about this concept, like mathematic derivations and more other models and applications. You can find this course as supplementary materials. About the policies and grading. So we totally have 2 assignments. Assignment 1 account for 20%, assignment 2 account for 30%, and the final exam is 50%. And for penalty will be applied to late assignment submissions. So 5% of total possible marks for that task is deducted per day. And if you submit 5 days later than the due date, it will not be accepted. So if you think you cannot submit it online, you can apply for the special consideration. And there is also a short extension application portal on the assignment submission page. So you can also apply for the short extension as well. So that's for the assessment part. And another notice is the assignment 1 will be due on the end of week 2. So that will be next Sunday night. So I would recommend you just start to work on it as early as possible, and lab notebooks from the first 2 weeks will be very helpful to assist you in completing this assignment 1. Okay. Is there any questions till now?
Yes. Hi, it's
Yes,
Kathy.
doctor.
Oh, sorry, doctor. Can I just quickly ask, is it a closed exam because last term it was open for some subjects?
It is a closing exam.
Okay, thank you.
With the assignment, doctor, how strict are you with the word limit? So I know that like the report is only 1,000 words.
There are some like recommended number of words for the assignment. That is just for your reference. It says if you write more words than the requirement, you won't
Yeah.
get penalty for that. So that is just a reference saying how much content that we are expecting. Like if you have much less words than that, like you cannot make a solid justification or explanation for the content. So
What
yeah,
if I write like 2,000 words instead of 1,000 words, like as you recommended?
if you exceed the limit, it doesn't matter. You won't receive penalty for that. No penalty for that.
Great. Thank you very much, doctor.
Okay. There are two reports, no? Task 1, one report, task 2, another report, and there is this code. This is the Python code. Is that right? There are 3 submissions. You have to put all that into one document or 3 separate documents?
There should both assignment 1 and assignment 2 requires coding and report as well. So you need to submit the code and the report.
So 2 reports and the code, no?
Yeah, just read the assignment instruction. So it should state that you need to submit both code and the report.
But assignment 1, it is clearly said that the code is not required. Assignment 2, the code is required.
Let me see.
Yeah, it says that don't attach the code. Assignment 1, I'm talking about.
If you go
Assignment 1, I don't know, how do you do without attaching codes?
I think you have to do the code, but don't attach. That's what it says.
you can see
Maybe to the report.
Yeah.
this is the assessment 1, right? This is the assignment 1. Assignment 1 details and instruction, and for the submission details, you need to submit your code and your report.
Yeah, but that's for the both 2 tasks. I'm talking about task 1. Yes, this is for all the tasks. The task 2 need code, but the task 1, it says if you go above, don't attach the code. It says task 1 somewhere there. Describe. It says the code. Do not attach code.
In the report.
Yeah, in the report. Yes.
Yeah, that's a report is separate. That's what it means, probably.
Yeah, that's right. But
Yeah,
the
you
same
don't
code for attachment 1 and attachment 2, no? Because you use the same.
I guess that I thought this is how I read it. That like you don't add the codes into the report. So like when you describe the first task 1 first question is describe the data set. When you describe the data set, you can run some codes, but you don't attach those codes to the codes when you describe that on the data set about on the report. That's what it means. That's
Yes, but
that's how I read it.
task 2 code is same as task 1 code. Use the task 1 code, then improve the task 2. So if you attach the task 2 code, that's enough. because task 1 is cleaning, that cleaning or the pre-processing, then you go to the task 2. And if you attach the task 2 code, it includes the task 1 work also.
Sorry, I don't get the question. So what is your current concern?
What
You
I'm
need to
asking,
submit
we have
both
to
code
roughly,
and report. And let's say for task 1, describe the data set. You need to run some, as the another student said, you need to run some code to get
yeah, right, yes.
the aspect of
Yes,
the
yes,
data
so
set,
that
and
was
then you need to write the result in the report. Report is used to be read by human, so
yeah.
it need to be organized as in a human readable format, not as the like code and result, not in the notebook
Yeah.
kind of style.
Yeah, that's right. Yes. So ultimately, you write a report 1, task 1 report, task 2 report, and the code. Three attachment. No.
Not really. You only need to submit the code and report. Report should include the expected content from both task 1 and task 2. So you organize this content into one report.
Task 1 and task 2 combined into one report.
Yeah.
All right. Okay. All right. Okay. That's fine. Thank you.
Another quick question: how soon do we get results of the assignments? This is in consideration with the 5-day late submission penalty. Is it within the 5 days, or you wait 5 days and then release the results?
So normally it takes 2 weeks to release the marks. If you apply for special consideration or the like the short let's see, the short extension, so the release date will be postponed a little bit. Let's say if you apply for the 3-day short extension, the release date will be 2 weeks plus like 3 days later.
So, Doctor, does the 5% penalty apply to the 3-day extension?
No, if you apply for the 3-day extension, those 3 days won't receive penalty. If you then submit later than this 3-day, then 5% will be deducted per day.
Yep, thank you.
Just a quick question. What's the level for AI usage in this particular course?
Sorry, what's the question?
What's the level of AI, generative AI use in this course? Is there a specific level, like no AI, AI planning, AI collaboration?
Are you referring to the assignment board?
Yeah, just in general, because usually we have that in all the other courses. They specify what level of AI we can use.
Here's generative AI use requirement at the top of the instruction.
So this is one of the lot, because in previous courses the lecturer chose for us. So I just want to confirm that in this case we can choose for ourselves.
What do you mean by choose by yourself? You mean what?
Is that which one we have to use? No AI or AI planning or AI collaboration or full AI? Like, please let us know which one. Then we will follow your instruction.
Which level is permitted?
Yes.
Okay. Okay. I need to double check with the subject coordinator, because this is I think the unit just migrate to this like AI allowance. Previous years we don't allow like AI assistance in the assignment. I need to double check with the coordinator. I will.
Yeah, that's important for some of us, because some of us use VS Code and run run some local models like Qwen and so on to help us coding.
Okay. Yeah.
Yeah, And also in previous subjects we've had this year, usually the subject lecturer and coordinator have always specified exactly which level it is. I think that's why I'm just asking the question for that reason, because almost like the last few courses I've done, almost every single course has specified it.
Okay, I will double check with the coordinator. Of course, tomorrow. We will then make an announcement about that.
Thank you.
Okay, all good. Then we can continue. Okay, here's some typical things that machine learning can
Sorry,
do.
sorry, doctor. At the bottom of this assignment page, there is a highlighted line with submission detail which says if you use ChatGPT or other generative AI tools, you must cite them and clearly indicate your original contribution. So, if that helps, anyway.
Yeah, thanks for pointing that out. Again, yeah, I will also double check with the coordinator because
Sure.
that is related to the report. I'm not sure about the like coding part, and so on. So
Oh, I see.
yeah, so I will double check with him.
Right.
Thank you. Okay, here's a list of some common tasks that machine learning will be very good at, like speech recognition, natural language understanding in narrowly bounded domains, image recognition, playing video games, robot locomotion, and drive safely along the curving road, and like machine translation, those kind of stuff. And here's just some a few of the commonly things that machine learning is good at. Let's watch a few videos to get like more intuitive understanding of what these AIs can.
Let's
machine
say
learning
you
can
want
do.
to ask Google to make you a haircut appointment on Tuesday between 10 and noon. What happens is the Google Assistant makes the call seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
So how can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like. What service is she looking for? Just a woman's haircut for now. Okay, we have a 10 o'clock. 10 a.m. is fine. Okay, what's her first name? The first name is Lisa. Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks. Great. Have a great day. Bye.
That was a real call you just heard. The amazing thing is the assistant can actually understand the nuances of conversation. We've been working on this technology for many years. It's called Google Duplex. It brings together all our investments over the years in natural language understanding, deep learning, text to speech. By the way, when we are done, the assistant can give you a confirmation notification saying your appointment has been taken care of. Let me give you another example. Let's say you want to call a restaurant, but maybe it's a small restaurant which is not easily available to book online. The call actually goes a bit differently than expected. So take a listen.
How may I help you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people when?
Next Wednesday at 6 p.m.
Oh, actually, we reserve for like after like 5 people. For people, you can come.
How long is the wait usually to be seated?
When tomorrow or weekday or?
For next Wednesday, the 7th.
Oh no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Bye bye.
Okay, just looks like a combination of speech recognition and the combination of speech recognition and chatbot. And another application is the real-time object recognition and object tracking task. So you can see that the model can recognize different type of objects, and it is also accompanied with like confidence level. Like there's a percentage alongside with the type of the object recognized. Okay, and machine learning models can also use to train this figure to learn its motion to jump over obstacles and make the right path to the destination. So it is more likely that this kind of task is done through the like reinforcement learning.
මොකද්ද? ඒක මට ඊමේල් එකට දෙන්නේ. බලමු මට මතක් කරන්න.
And
百度在18
the
年
next
前创业，
application
赶
is
上了
about
互联网的浪潮。
the machine translation. It translates the sound into the text, like it converts the sound into text.
2000年，当时中国只有1000万互联网用户，今天中国的互联网用户已经超过8亿了。AI 对于社会的影响将远远超过互联网。过去的20年，我们都感受到了互联网所带来的变化。接下来的几十年，我们将体验到 AI 给社会所带来的更加深远的影响。
Okay, this is another application. Okay, is there any questions till now? Okay, let's continue. So we have seen those applications for machine learning. Then what is the definition for this machine learning term? So the machine learning a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task in T as measured by P improves with experience E. This is like very abstract definition, but we can see some keywords from it. So for machine learning method, learn and improves are some two features for this kind of method. And it need to rely on the experience. It need to know the specific task, and we need to give it performance measure so that it knows if the performance is improved or not. So let's see more definitions, but explain it in plain language. So in short, machine learning refers to computational methods that use experience to improve performance. For example, to make accurate predictions. So experience here means data-driven task, the statistics or probability. An example of machine learning is to use the location and the size of house to predict its price. So let's just take this house price predicting as an example to see where this keywords relies in. So for this house pricing prediction, the task would be to predict its price, right? And the experience is the data. So what kind of data we can get is the information for the houses, right? We can have many different houses. It may be located in different area. They all have different number of bedrooms, different sizes, and if they have like car park or not, car space or not, and those kind of characteristics. And all those characterizing informations are the experience that are going to be used in the machine learning. And the performance is how accurate that the model can make the prediction for the house pricing. And we also need, like we said, also need a performance measure. So here in this example, we need to measure if the predicted price is close to the real price for this house, so that we can measure how well the machine learning model performs. And we can say if we need to further improve the model's to improve the model's performance. So in computer science, machine learning requires the design of efficient and accurate algorithms, the analysis of complexity, and theoretical guarantees. If we look back into the history of machine learning development, we can see that it can be traced back to the 1750s to 1900. So at those times, the popular method would be the Bayes theorem and the least square method. And later on, it also developed the PCA method and also like K-means method, that is for clustering, a very classic clustering model. And the nearest neighbor model, that is for classification model. And later on, just until the 2000. And we can see that before 2000, they're all related to the conventional machine learning models. And later on, since 2000, we have defined the deep learning structures. So the model becomes more and more complex since that time, and we have more data available, we can get more data through the internet, and we have more powerful GPUs, then those factors enable us to develop more and more complex deep learning architecture, and then perform much better performance later on. And nowadays, popular large language models like GPT and the cloud, and those models are all deep learning models. And we have seen the power they got nowadays. So let's see what is machine learning in our real world context. So machine learning will involve designing algorithms that use data to programmatically learn a model of it. And the learned model can be used to detect patterns, structures, themes, trends in the data. So we can like train models to, let's say, do the stock price prediction. So we can predict the trends for the stock price. And we can also make prediction about future data and make decisions. And the model machine learning algorithm are heavily data driven. So that means it doesn't need to hard code all the rules. We don't need to have a like thorough understanding of how all the possible pathways that the system would go, and we don't need to list all the like infinite number of possibilities that the task we will meet. And the rules are not static and can adapt as the machine learning algorithm ingest more and more data. So this is one of the features for the machine learning algorithms. So it requires a lot of data so that it can infer those invisible rules through the learning process. And the machine learning will involve like would have two phases, like training phases and predicting phases. So machine learning is about using data for answering questions. So using data is more related to the training, and answering questions is talking about the prediction. And how can we connect these two phases together is through our trained model. So when we ingest many data in the training phases, the output for this training phases should be the model. And normally we refer this model as function model F or mapping function F. And with this model F trained, and we can use this model F to do the future prediction. So that means when new data comes, the new data will be fed into this function F, and then the function F will be spitting out the prediction corresponding to the input data, and that would be the new answers for the new input data. And you may have heard of like many popular words like artificial intelligence, machine learning, deep learning, and also their abbreviations, and also something like computer vision, CV, natural language processing, like NLP. So you may have heard of many of these kind of big words. And so what are the relationship among them? So artificial intelligence would be a very big word. So involve like everything or all the systems or all the programs that can express certain level of intelligence. And if those systems can express a certain level of intelligence, and it can be called artificial intelligence. Like even for some program, conventional program, like in those program we handmade, we list all the handmade rules in the program. Like we read many like if else clause. If you do the coding, we read many if else clause to direct the workflow inside the system. Even in those kind of classic system, it can also be called artificial intelligence, because if we view this system out of the box, it shows some automatic decision-making abilities through its performance. So those can also be called artificial intelligence. This is a very big word. And under this big word, there's a subset called machine learning. So this machine learning, those methods referred by the machine learning concept has one common features, that is, it learns those rules from the data. It requires many data to infer those invisible rules by itself, and it doesn't require the user or the programmers to list all the to hard code all the rules to get the workflow. And under the umbrella of machine learning, there's a subset called deep learning. So those deep learning methods are all built upon similar structures, that is neurons and edges. So they are called neural networks. So the structure of these models are very deep, and the computation will require a lot of resources. And since these characteristics of this subset of methods, they are called deep learning, and that is our modern machine learning models. And more specifically, we refer these models as deep learning models. So the relationship between these three words would be AI would be the superset of machine learning, and that would be the superset of deep learning. Okay. And here's the paradigm of machine learning. So we have seen this function f again, and this is the model we want to train. And by the end, ideally, we want to provide input data to the model, and we are expecting this model to spit out the corresponding label or the objects contained in these images. So that is what we want from the model. And how we get this model F trained is through providing a lot of historical data along with its label, with true labels to the functions during the training phases. So this is the training phases, and we need to provide this data to fine-tune the model so that its performance can be iteratively or progressively improved at the end of the training process. And then after the training process, it is ready to predict labels or predict outcomes when we provide new unseen input data. And this is the predicting phases. And to abstract this paradigm of machine learning, we can see that it is separated into training phase and prediction phase. And during the training phases, and these samples are just corresponding to this historical past data. And to feed these samples into the machine learning model, first we need to do the feature extraction. We need to extract some useful information from the raw data and to generate bunch of feature vectors. And these feature vectors are the actual information we will feed into the machine learning models for training. And for this training process, it should also accept, especially for supervised learning, it also need to we also need to provide labels. That is the true label corresponding to each sample. So for this example, so we need to during the training phases, we need to provide the individual image, and we also need to provide the corresponding labels. That is saying what objects contained in this image as the label. So we need to provide the pair, the image and the label pair to the model. And similar for this one, we need to provide both sample and their corresponding label to the machine learning model. So this would be the model F. So after the iterations of update, the model F would be get trained well and become trained classifier that would be as noted as F star, and this is the trained model. So with this trained model, it is ready to make prediction for new input. So when the new input comes, we need to do the feature extraction again because the information fed into the machine learning model is the feature vectors. So we also need to provide the feature vectors to the trained model. So it need to go through the feature extraction again to extract the useful features, and then the useful features are fed into the trained classifier or trained model F star, and then the function will spit out the corresponding label for this new input. So that is the paradigm of machine learning. So is there any questions till now? Okay.
I was a bit late to hit the audio button. Quick question about the previous slide.
Yeah.
The feature extraction, is that the same one as the one that was in the training phase? Is that actually machine learned, or is that hand created feature extraction?
Good question. Handmade features and automatic feature extractions, they are two different paths. Both of them that has been used in real world projects. So but handmade feature extractions are more about the conventional way, and automatic feature extraction is more like how the deep learning models are extracting those features. We will see that later in the second half of these subjects. Like for CNN models, they are using convolutional layers, and these layers are used to extract features, different level of features. And what kind of features those layers can extract, it depends on the data. It will depend on the training phases. In different training phases, those feature extraction layers will be adjusted, and in different iterations, they are going to extract different type of features, and those feature extraction layers are also the parameters that the deep learning models are going to tune so that it can find the best feature extractors that fit the specific task the models are going to solve.
Yeah, that makes sense. So in that diagram, is that feature extraction also being learnt, or is that because it looks like it's just a static box?
Yes, this is just like general abstraction for this workflow. So this feature extraction can be part of the model. But for deep learning model, the model definition will be like this. This will be the whole model. The model will have some few layers that doing the feature extraction inside the model itself.
Got it.
But this illustration is more like the conventional workflow for how to train the machine learning model. So we have explicit feature extraction process, like a pre-processing stage, staying there, and then to extract the useful features, and then these feature vectors are going to be fed into the model. And we can also combine these two methods because if you have some domain knowledge for the task, you also provide some handmade features to the deep learning models, and it will sometimes it will very helpful, more helpful than just simply providing the raw data into the deep learning models.
Thank you.
Okay.
Sir, one question here. So who will define those features? Like, for example, like if it is just simple numbers or something like that, how that feature will be, how will the model understand this? Yes, this is the feature I need to pick it up. Or if we are showing feeding a car to be identified as a car. So who
Yes,
will,
that is the
how the
good
model
questions.
will,
But we can keep the questions and answer that in a few slides later, when we talk about some specific examples, and we are going to talk more about the features. But at current stage, you just need to know that the features is just kind of information that can distinguishly describing one sample data. Let's say for let's say if we are doing the housing price prediction task, and the data should be the feature of a house, right? So what are the features? The features would be the number of beds, the number of bathroom, the size of the house, and the years old, how many car spaces, those kind of informations. So different house will have this side of information, right? So these feature informations are used to distinguishingly describe each individual data or sample. Does it make sense?
yeah.
Okay. Let's come back. Okay, so what kind of task would machine learning solve? So there are a few categories. So the first type of machine learning task is classifications. So this kind of task, a few examples would be belongs to this task would be spam detection and face recognition. So what classification task is doing is to predict a category. So let's say we have this kind of 2D coordinate system, and we have scattered point distributed in these spaces. And all these points belongs to either blue groups or the red groups. We have known this group belongingness beforehand. And now we want to know the rules, the invisible rules, how let's say the system decide which for certain points why it belongs to blue, not red, or the vice versa. So we want the model learn these invisible rules so that later on, when new data point comes, maybe the point is here, and we want the model to answer the questions, which group this new data belongs to. So for this classification task, we want to train a model that can make a prediction about which group the new data belongs to. So that is the classification task. So for spam detection, so we want when the new email comes, we want the model to predict if the new email is spam or not a spam. That's the two category or two groups we want to predict. And for face recognition, we may want to, let's say for iPhone, we need to unlock the phone with the camera. So the phone will take a maybe picture for our face and to recognize to make a prediction if the face is the owner's face or not. So that is also a classification task. And we have talked about this. So for email spam recognition, so when the new email comes, we want to categorize the new email into a few categories. So it can be spam or not spam, or we can have more possible categories, saying spam, or is it should go to the primary inbox or social inbox or promotion category. So we may have more than two categories to classify. If we are only interested in two categories, so that would be the binary classifications. Let's say if we want to train a classifier that is going to predict if the new email is a spam email or not a spam email. So that is binary classifications because there can only be two possible outcomes, either spam or not a spam. And for face recognition, if we are interested in if the picture is the owner's picture or not owner's picture, it will be the binary classification problem. But if we make the problem more complex, if we are interested in what's the identity of the person in this picture. So that means we may have many possible outcomes. So because we may have like for this live session, we may have like 67 different persons. That means we will have 67 possible outcomes corresponding to each individual or each one's name. So when the image come, we are expecting the classifier to predict what's the name of this persons. So the expected, the possible outcome will be more than two. And in that case, it will be multi-class classification problem. And again, for the training, we need to provide the face image and the true label so that it knows for each label what would be input data would looks like. And the classification model would learn those invisible rules or underlying rules so that when it meets the new image, based on these rules, it can make the prediction for the identity of the person. And what if the model cannot not only predict just one label? What if it can predict multiple labels? Let's say if we are given an image of this dog, and then we are expecting the classifier or the model to make multiple predictions. It can say it is dog, that's true. It is puppy, that is also true. And it can also say it is Shiba Inu. So it not only just predict one label from this image, it can predict multiple label from the same image. And in this case, it is multi-class, multi-label problems. Okay, is it all right for this classification task?
Well, for that last one, when you said I thought it was like one. You remember how you showed the video of Google having the car, human, car, human? Is that the same as this one as well? Multi-label. When you have one scene, you've got cars and people, and it can identify that that's a person, that's a person, it's a car, that's a car, that's a dog. Is that the same?
Not really. That should be the multi-class classification. For it would be, let's find. So you're referring to this one?
Yes.
Yes. You may have seen that this kind of prediction is flashing, like changing from one prediction to another prediction.
Yeah,
That may be some like wrong prediction or wrong tracking for the
but
result.
it
It's
was a
not.
static image. It was a photo. Would that still be multi-class if it could identify everything, all the objects? Like,
Yeah, maybe for like for this same scenario, if for multi-class, multi-label prediction, it would say person 27%, maybe male 50%, something like that.
oh, so the actual object, multiple labels on the one object. So the person.
Yeah, yes, yes.
Okay, that's what you mean. Okay,
Yeah.
thank you.
Okay. I think we can have 5 minutes break, then we can continue. Let's come back at 9:07. Is that all right? Okay, let's come back and continue. So we have seen the classification task, and now let's look at the second machine learning task that is called regression. So what regression is doing is it is asking the model to predict a number, such as house price and temperature prediction. So the expected output is a continuous number instead of like one out of the possible outcomes, like one of the categories as stated in the classification task. So the output of regression should be a continuous number, not one of the category. So let's look at an example. So here for housing price prediction, and it should be a regression task because we are expecting the output from the model should be the price of the house, and this price is continuous. It can be like any number, but in real world it should be a positive number, but it can be any continuous numbers for the house price. And we also have the label, and the label should be the true price for the house. And we also have some features informations like the number of bedrooms in the house, the number of bathrooms, the size for this house, and the miles to downtown, and miles to some ski resort mountains, and other informations like car space numbers, the years old, and so on. So these informations are going to be used to distinguish different houses, and all the house should have different set of these features, and these are called the features, and these informations are going to form a feature vector, and this feature vector are going to be fed into the model for training and also for prediction. So the input should be the feature vector, and the output should be the label or the prediction. So the comparison for the two tasks we talk about is the regression and classification task. So for regression, the labels are continuous and ordered. So continuous, well, we know that we can have like any numbers, like let's say 300K, or we can have like 300.5K, those kind of numbers. So those output are continuous, and these output are also ordered, and we know that the 1.2 million is larger than 324K, so they are ordered. In comparison, for the classification task, the labels are categorical. That means they are not ordered and the values are discrete. So we cannot say class 1 is superior than class 2 or class 2 is superior than class 1. There's no such relationship for the predicted output or the categories. The only meaning for these 4 different output is that they are representing different categories. So they are different, but they are not ordered. So we don't have such kind of greater than or smaller relationship between the categories of the classification task. So these are the comparison between regression and classification task. For both classification and regression task, these are categorized as supervised learning. So why is because supervised learning will require label come with the data. So that means when we do the training for the supervised learning model, so we need to provide both the input data and the true label. Let's say for house price prediction, the input are these feature informations like bedroom numbers and years old, those kind of information. And the label is the true price for the house. And this pair should be provided as the input or the training data for the supervised learning models. And also for classification task, we need to provide the image that is the actual face for the person, and also the name of the person in this image. So this we need to provide this pair to the model for training, so that when the model do the prediction, when it sees the image, it can predict the corresponding label for the image. So these are supervised learning method or models. And another type of machine learning task is unsupervised learning. So as the name suggests, in comparison with supervised learning models, unsupervised learning models doesn't require labels. So one popular task is the clustering. So what clustering do is it discover groups in this data when labels are not available. So just ignore this colors in color and area in this coordinate system. So imagine that we just have some gray scatter point distributed in this space, and we want to find the patterns in this data. Let's say we want to answer a question like how many groups belongs to reside in this space. Like is there any natural group that this data belongs to? Then we may just find that this data can form two distinct groups. Like one is this blue groups, and another one should be this red groups. And we don't know the actual belongingness beforehand when we do the training for this machine learning models. We don't know that this data points belongs to the blue and this data point belongs to the red. It is not like the classification. For classification task, we know that this data belongs to the blue groups and this data belongs to the red group beforehand. But for clustering task, we don't know the belongingness beforehand. We just know that points are distributed like in the space like this, and we want to know like how could they form two distinct groups, and the model will learn how to divide them into two groups. And this is the group belongingness is just the final the learning outcome. So that is the clustering method and also the unsupervised learning method. So those methods doesn't require label beforehand. And as I said, clustering is just one of the unsupervised learning tasks. And the input will be some vectors x1 to xn. So each x will represent one, you can treat it as one scatter point in this space, 2D space. And the number of clusters is how many groups it can form. So in this case, the K should be 3 because we have 3 distinct groups and colored in 3 colors in this space. And the output from this model would be the belongingness for each data point. So the model should answer which group x1 belongs to and which group xn belongs to, and the answer is stored in y1 and yn, and the value for this y1 and yn should be one of the values from the cluster index. So let's say in this example, we can say maybe this point is x1, and then y1 would store maybe 1 representing the red color, and this may be x2, and the corresponding y2 would be let's say 2 representing the blue color, and this may be xn, and the corresponding predicted class yn maybe a store value k corresponding to the green. And here k, in this case, it should be like 3 because here we assume the k, we set the cluster number k as 3 because we only want all this data to form 3 distinct groups. Okay, for the comparison between supervised learning and unsupervised learning is supervised learning learn function from label training data. So the training data come with the data and its true label. So classification and regression are supervised learning task. And for unsupervised learning, it draw inference from data sets consisting of data without label. So for unsupervised learning, we only provide the data itself, and we don't know their true label. So in that case, we are using unsupervised learning models, and clustering is an unsupervised learning task. So this unsupervised learning is normally used to find some unknown patterns or to draw some insight from the data. So in that case, we don't know what we are looking for or what kind of labels the data would come with. So in that case, we are using unsupervised learning method.
Benefit of removing labels from it, let's call it a supervised set that's fully labeled, and trying to derive, I guess, more insights or understanding of the data by going through an unsupervised method. Would you ever do that?
Not really. Like I would say supervised learning would be more
beneficial,
reliable, I would say, because you know the true answer. Like we know it's like we are learning our learning experience. We do some practice and we know the true answer, and then we gain some experience from this exercise, and then we go to the final exam. In that case, we don't know the answer, but we can generate some answers during the exam. It's like that. And for unsupervised learning, it's kind of like exploration. We just try to find some patterns in the data, but normally we don't know the true answer. We don't know what we found is true or false because we don't know the true answer. But we believe we find some patterns from the data. That's what data says. So it's kind of that. So unsupervised learning is more like exploration or something. If the data come with true label, that's great. If data doesn't come with label, that leave us no choice to choose the supervised learning. We can only choose unsupervised learning. And there are also like semi-supervised learning and self-supervised learning that is beyond our scope of these subjects. But just for your information, like semi-supervised learning is kind of a mix of supervised learning and unsupervised learning because we have a small amount of labeled data and we have large amount of unlabeled data. So we use the labeled data to do some supervised learning and then to infer the label of unlabeled data so that we have like more labeled data to train the model. So that's kind of semi-supervised learning. And for self-supervised learning, it's kind of, we don't have a label beforehand, but we ask the model to generate your own label and you do the training and so on. It's kind of like that. Does it make sense or it is more confusing?
No, it makes perfect sense. I guess all I wanted to understand is, would there ever be a real scenario where, let's pretend you know that your images are dogs and cats and whatever, koalas or whatever it might be, but would there be any benefit to remove the labels and just see what, let's say, the machine tries to derive? But what you're saying is, no, it's kind of nonsensical. It's best to train it on the labels and then work from there, right?
In most cases, yes, supervised learning is better than unsupervised learning for that. Let's say for the dog and cat prediction or classification, we know the answer. We know the true label for each image. We assume that the true label is correct. In that case, the supervised learning would be best suited for this kind of task. And we can also do the supervised learning for this kind of task. Let's say we have a bunch of dog and cat images, but we don't have label for each individual image. We can do the unsupervised learning for that to try to separate these images into two groups and hope that one group is for dog and one group is for cat. But that is not reliable. Maybe the two groups representing color image and black and white image. So we don't know. Right?
Yeah, understood.
Yeah. Okay. And there's another type of machine learning task that is dimensionality reduction. And the purpose this kind of task is to compress data into fewer features while keeping the useful structures. So we have seen that the machine learning models sometimes the machine learning models accept feature vector as its input for training, and sometimes we may form a very long vector that is high dimensional vector, maybe for some data science or data analysis projects. The input each sample will have like a large number of different features, and if we form them all into a single input vector, it will form a very long vector. And in that case, not all of the informations are useful, and some of the information may be redundant or highly correlated. And in that case, we may expect to have some kind of method to reduce the size of this vector so that we can also make our model less complex and reliable and easy to train. So we can, in that case, that is where the dimensionality reduction plays like key role. So it will reduce a high dimensional vector into a low dimensional vectors. So it is useful for visualization and analysis. Let's say you have many data points in high dimensionality, and it's hard to visualize their relationship or distribution if the dimensionality is greater than 3. At least I can't imagine how a 3D data point will distribute in my head. So we can reduce the dimensionality of the data into 2 or 3 so that we can draw them in a 2D space, just like a data point like this. If we reduce each data or each high dimensional vector into a 2-dimensional vector, we can represent each data as a single data point, and then thereby we can see their distribution and maybe potentially find some patterns or validate if the discovered pattern is meaningful or not. So that is for visualization and analysis. And for data processing, as I said, we can reduce the input feature vector size so that it can make the training of the machine learning model more efficient and accurate, and the complexity of the machine learning model will be reduced. And there are some methods for dimensionality reduction, so PCA and kernel PCA, that would be many very popular conventional way to do the dimensionality reduction. And autoencoder, that is the more modern way, especially for deep learning models, to do the dimensionality reduction. And PCA is a linear method, and autoencoder is a nonlinear method. So it is more it is more flexible or have more freedom to comprise the data than the linear method. And if we combine the supervised and unsupervised learning, or let's say combine the usage of this classification regression clustering task, it can also achieve the ranking and recommendations task. It is more complex or requires the cooperations of the previous tasks. So let's say you may have seen the, let's say, YouTube channels. You will receive some recommended videos to play as the next video. So it will utilize the recommendation systems. So the YouTube will have like billions of videos available to suggest for you, but we cannot just simply compare like generate a recommendation score for all these billions of videos in a single run because it takes a lot of time. So we may just find clustering of maybe user preference or based on your habit and group the users into some predefined subgroups. And these predefined subgroups will be discovered by the unsupervised learning or clustering. And then the suggested videos maybe number of suggested video may be down to 100 and 1,000. And then we can generate some recommendation score or some preference score using the regression method. And then rank those videos using the recommendation score. And then maybe play the next video with the highest score to the user. So that is the ranking or how the ranking and recommendation system would generally do. And there are many other methods specifically for these two kind of tasks. But yes, these two are also the common task that the machine learning models would solve. And another popular type of machine learning task is reinforcement learning. So you may have heard of this AlphaGo system. So it can beat the like human champions in this Go game. So it is using the reinforcement learning. So what reinforcement learning do is it learns a sequence of actions by trial and error. And as in game playing or robotics. So let's say assume we are playing the Super Mario games. So we the characters are interacting with the environment, right? It needs to jump over the obstacles, or if it hits the monsters, the character would die. So with this kind of real-time feedback, the model learn how to adjust its movement so that it can receive the highest possible reward or the scores while it playing the games. So through this trial and error process, the robot or the agent learns how to achieve the best performance. So that is another type of machine learning task, reinforcement learning. So how can we use the machine learning models to solve the problems? So what is the workflow for solving machine learning problems? It's divided into these three aspects. So at first, we need to identify the task. So what task are we going to solve? Is it a regression task? Is it a classification task or clustering task? So we need to abstract the problems and formulate it into a machine learning task. We need to understand that do we have the data with label or not? If it comes with label, then it definitely we can use the supervised learning models. If it doesn't come with the label, we cannot use supervised learning. We may can only use the clustering method or other unsupervised learning method. So we need to define the task or identify the task first. And then with this task decided, we know that there are some specific models that are used to solve this kind of task. So for classification tasks, we know that we can use neural networks. We can use SVM. We will learn that later in next week, like support vector machine and logistic regression. Although it has the regression term in its name, it is a classification model, not a regression model. And we can use decision trees or nearest neighbor. So these are some models that we can choose from, and we need to know their pros and cons so that we can choose proper models to solve the problem. And then with the task and method decided, we need to choose the algorithm to solve the model, or can say to optimize the model or to tune the model parameters. And there are gradient descent model, stochastic gradient descent, and Newton's method. So these are all optimization methods that we can use to optimize model or say fine tune or tune the parameters of the model so that we can get the trained model more efficiently or accurately. And so what enables the development of modern machine learning models? That is the availability of the large amount of data to train the machine learning models and increased computing powers like GPUs. So with the popular of the internet, and we have a lot of information and data available through the internet. We can, like back in 1990s or early 2000s, we don't have that much like photos or digital documents or those kind of information available on the internet. And so that since machine learning models data eager, it requires a lot of data to train to get a better to get an acceptable result. So since we don't have those data available at that time, so it's the development of modern machine learning models were postponed. But now it's not a problem anymore. Now we have like too much data available. And it already makes our like training requiring a lot of computing resources. And regarding the computing power, if we are just using CPU to train the model, because CPU is doing the first task or computation process sequentially. If we train the model on CPU, it will require a lot more time than training on GPUs because GPUs have many small units or cores to do the parallel computing. It will speed up the computation speed by 10 to even 100 times. So when we get a model through CPU, it may require like weeks or months to get a result. And if we train the model on GPUs, we may get the trained model in hours or days. So that's a large boost for the development of modern machine learning models. So when we are talking about the modern machine learning models, we are actually talking about the neural networks. So we can see that these are all different models, and they all present like similar structures. Like they are built using these nodes that's neurons and edge, and the difference is they are presenting different number of layers. Each layer may have different number of nodes, and that's the difference. And there are also some like computing units reside in this nodes. That's some other difference. We'll talk about that later. But here we just need to know that for modern machine learning models, we're talking about the neural networks. They just present different architecture for this node and edge distributions. And with this model defined, we will define a loss function. And the loss function will be just a comparison between the the model generated prediction and the true label. So we compare the difference, and we want to minimize this difference. And in that case, we need the optimization method, and that is what this algorithm do. So they are going to fine-tune the parameters in these neural networks so that the neural networks will generate a result that is closer to the true label. So that's the difference between true label and prediction will be minimalized. And you can see this curve shape, which just corresponding to the difference between prediction and true label while setting different parameter values. Here is just simplified version, and we can see that it has only two parameters to tune x and y, and the loss function value would be just changed corresponding to different x and y. And the simplest model, or the first model we're going to meet, would be the linear model. So here, the feature vector would be defined as a vector, a one-dimensional vector. So here is that x belongs to RD. So that means x is a column vector. And each element in this element, we can number them by this. So there will be in total D elements in this column vector. So normally, if we don't specify if it's row or column vector, it means that this feature vector is a column vector. So each element will corresponding to one feature of the data. So what does it mean is, let's say for the house price prediction example, this X1 was corresponding to like the number of bedrooms, and X2 would be corresponding to number of bathrooms, and X3 would be square feet. And there are many other features. We just write them and form them into a column vector. We may say it maybe for one data, we may have like 3 bedroom, 2 bathrooms, and it may have like 1,000 like square feet and so on. And we will get this kind of feature vector as the training input or the input data. How can we convert this input into the output? Is through this function. This is the definition for the linear model. So what it means is it is a linear combination between the weights and the value for each individual features. So we have W1 that corresponding to the weight for feature X1 and W2 for feature X2 and so on. So since we have D features, then we should have D different weights. So you can think of it like the importance or the contributions for each feature value. So you can say X1 is the number of bedrooms. So that says this fx would be the price. It is the predicted price from the model. So to get the predicted price, how much contribution would this number of bedrooms will contribute? And this how much is defined by this W1. So this each weight will define how much contribution would this each feature values will contribute to the final summation. And the summation would be the final price. And this is the linear model. So again, linear model is just the linear combination between the feature vector and the weight vector. And if we expand it, it will be just this kind of multiplication and the sum. Okay. Then how can we find? Because all the informations in this X vector is given by the feature values, right? We know these feature values beforehand. Like for each house, we know the number of bedrooms, we know the number of bathrooms, we know those values that formulating this X vector. But what we don't know in this equation is the W. So we don't know the value in this W because we want to get the FX, that is the predict price, right? We already know the informations in this X. And now we need to know what the values in this W vector. So if we know the values in this W vector with this multiplication calculation, we can get the price for specific house. So how can we find this W? That is going to use the optimization algorithm or those gradient descent method. So first, we need to define the loss function, right? We need to define a measurement to measure how much difference do the prediction differ from the true housing value, true housing price. So this is the definitions for this loss functions. So what it means is xj t multiplied w. It looks similar to this definition, right? So that means for the house J, for the house index J, what's the price, predicted price for this house? So this term means the predicted price for house J. Not J, for house I, And yi is the true house price. And we do the minus. That is the difference between the prediction and the true price for house I. And we square it because we want the difference to be a positive value instead of possible negative values. So we square it. And then we do this we calculate this difference for each price. It's iterate from house 1 to house n and calculate the sum. So that is the total difference between the predicted house price and the true house price. And we divide this summation. We divide this summation with n. So that is the average difference between the prediction and the true price. So that is the definition for this loss function. With this average prediction average difference gained, we want to minimize this average difference, right? We not only just want to minimize difference for one specific house, we actually want the model to make accurate prediction for all the houses. So we want to minimize this average prediction difference, right? So we are going to use the least square regression method to minimize this difference. So that means we want to find a value W, and this set of W values can minimize this loss value. So that is just a notation for this plain language. And to solve this least square regression, we will use the optimization algorithms that we will learn later. So here is just give you some taste about how we transfer problem into some mathematic notations and mathematic problems so that we can use the machine learning models to solve it. You can see that this is using the linear model to solve the house prediction problems. What if we are going to solve the the person recognition problems, can we still use the linear models? We can mathematically, but the result would not be very good or acceptable because for linear model, if the input is a photo, it will treat each individual pixel as a feature. So for image or for a picture like this, maybe it is dimension is 100 by 100. So in that case, we will have 10,000 features from the feature vector. So we will have a feature vectors with 10,000 elements, and we will train the model using these feature vectors. So what does it means is, so what each feature means is the linear model will ask each individual pixels to vote for the age for this person in the photo, and then the final age will be just the average of those or weighted average for those pixel weighting. So it is not reliable because the face of the person may be shifted a little bit, or if the person maybe look to the side, or maybe we can only see the side of the face. So those picture contributions are very different in this context. So so in that case, using linear model to solve this problem is not reliable. So in that case, we need to find some ways to extract some reliable features that is resistant to those like rotations and shifting process. So in that case, we are going to use the convolutional neural networks. That is our week 5 contents. So we will learn how to use the convolutional neural network to extract different level of features. We can see that we can define a few layers of convolutional layers, and each layers will extract different set of features, and those features exhibiting different level of information representing to describe the image. And we can see that with the low level features, it is more like extracting some edge informations or the shape and color distributions from the raw image. And the mid-level features is kind of the combination of previous or low-level features, and it draws more. It is extracting more abstract and not that human readable features, but it's machine readable features to fed into the model. And later on, for high-level feature, it is even more abstract, but it will be very useful for the model to make the classifications, although it is not that like human readable. But these features are determined during the training, and it is not like preset or predefined feature extractors. So we don't know if extracting certain like edge features will be useful or not, and the model will dynamically find what kind of features it will extract would be useful for classifying the image. So we will learn that later in week 5. And another application for this convolutional neural networks is for medical diagnosis. So for this kind of imaging related task, the input is an image, and the CNN models would extract some features from the image and combine those features to form a reliable prediction at the end. So it can answer questions like, is it a skin cancer or is it benign or malignant? So for this kind of task, so can you tell me what is it? What kind of task it is solving? Is it classification, regression, clustering? Is it which task this model is doing?
Classification.
Yes, great. It is a classification task because it is answering like which category this image belongs to. That's good. And here, this kind of model has already been developed in this paper, and accuracy is same. It achieves same accuracy as the human expert. And the CNN models can also be used in self-driving cars, so it can be used to recognize the vehicles or the environment on the road, like recognize the signs, cars, pedestrians, obstacles, and it can also, in that case, it can also track the speed of the car in the front. So it is helpful for the self-driving car system. I'm not going to play the videos, and the link is here. If you are interested, you can take another look. And for recurrent neural networks, that we are going to go through that in week 6. So it is suitable for sequential data, like for time series data and text data, speech data, and the large language models are just the advanced models for this series of models. So RNN is the basis models for all those advanced models. And it is useful for machine translation. And we have seen what kind of models we can use. So first we need to define the task to know if it is regression, classification, and we have many models to select from. Like we have linear models, we have CNN for computer vision or for image kind of task, and we have RNN for language, text, or those kind of sequential data. And with this model, there are two things we need to define. So what is the loss function? So how can we measure the prediction and our expectations? So with this difference defined, we can minimize those difference so that we can get a model that can achieve the lowest difference. That means the model can achieve accurate predictions. And with the model defined, it's time to solve the model. And to solve the model, we need the optimization algorithms. So we can use the gradient descent and stochastic gradient descent. So we will learn that in later weeks. And there are some computational challenges for this machine learning and deep learning tasks. So first, we have too many training samples. Like for the popular ImageNet dataset, it has 14 million images, and each image comes with size 256 times 256. We need a lot of space to store this image data so that when we need it, we need these images ready in hand. So we need a lot of space to store them. And the modern model becomes larger and larger. And for example, for ResNet 50, that is a popular CNN architecture model. So it has 25 million parameters. So that means to tune the parameters, we need to tune 25 million parameters to affect the result. We need to know how to set proper values for these 25 million parameters so that the model can generate our expected outcomes. So that requires a lot of computation. So the combination of big data and big models bring the computation challenges. And training this ResNet 50 on ImageNet on a single GPU would take around 2 weeks. So that's why we need efficient algorithm and software systems. How can we make more efficient algorithm and software systems, we can improve it from two aspects. One is modeling and one is computation. For the modeling, we can choose the proper model that fits better for the data and problems. Like for some kind of you may know better about the problems. You will have the domain knowledge, so you know the complexity of the problems. So you may choose the proper model for the problems. You don't want to use overly complicated models for a simple task, right? In that case, you will bring too much complexity to tunes during the training, and sometimes you don't have that much data to help you to train the model. So we need to find the model that fits the data and problem well. And we need to decide the network structure, activation function, and loss function. We will learn that later. And we need to improve the prediction accuracy. It is helpful that we have like hands-on experience in machine learning models. And if we learn, if we understand better for the problem and data, we know it better, it will also a boost to improve the prediction accuracy because we know where would be the gap resist. Another aspect would be the computation. So we need to design or apply efficient algorithms for those optimization algorithms. Sometimes is quick but less accurate. Some other method is slow but can generate accurate results. So there is a trade-off between using different algorithms. And we can implement the algorithm using systems like TensorFlow and Hadoop and so on. In this course, we are going to use the TensorFlow framework. And you can also optimize your code that would require experience in those algorithms and experience in the systems. Like sometimes you need to adjust settings for those algorithms so that it can achieve the best trade-off between the computation time and the prediction accuracy. And is machine learning or AI dangerous? I would say yes, it's dangerous, but it should be used with regulations and monitoring. But it depends on the usage. Like if someone use the machine learning or AI models to like mimic someone else's voice and do the telecom fraud, that is dangerous. If you just use it to assist your work, improve your efficiency, and to like make our life more easier, that would be beneficial. So that's debatable. So you can have your own opinion for that. Okay. At the end, let's just do this 4 questions quiz quickly. So for question 1, what is machine learning? So which options would you choose?
D.
The selective acquisition of knowledge using manual programs.
D.
Okay. I would say the D, the last option, the autonomous acquisition of knowledge using computer programs, right? Machine learning is computer programs, so we must choose from like B and D, and B is kind of like manual process to select the knowledge, but machine learning is inferring those knowledge or invisible rules from the data, so it do the automatic autonomous acquisition of knowledge, right? So I would say the answer is D. But for second question, machine learning is a subset of
D, AI.
Yes, the second option. So B, artificial intelligence. Okay. And for third one, what are the types of machine learning?
D,
All of the above.
Yeah, all of the above. And for last question, learn from test data that has not been labeled, classified, or categorized?
Unsupervised learning.
Great.
Mm.
Unsupervised learning. Okay.
Unsupervised, yeah.
Yeah. Okay. Last is Tesla autonomous driving that is using the machine learning models. I will just leave it to you. Okay. That would be all for today's lecture. Here are some reference for you to read. Those are optional. Okay. Any other questions? I see a lot of chat here, but I don't have time to walk through them all. But if you have any questions, feel free to ask.
Is the lab gonna be in Colab or is it gonna be
Colab. You're going to use the Google Colab.
and that uses TensorFlow?
Yeah. In the second half, we are going to use TensorFlow to develop the deep learning models. But for the first few weeks, we don't need TensorFlow.
Okay, so we can use Google Colab for the first 3 weeks.
We will use Google Colab through all the weeks. But
Okay.
yeah, but we will only use TensorFlow from week 4.
Okay. And the labs are already up on the
Yeah,
LMS?
yeah. The notebook is already there. You can upload the notebook to the Google Colab, and you can do all the development and running the code on Google Colab. It is more convenient, and you don't need to set up the working environment. That is a tedious process.
Is it permissible to develop it on one's own machine in VS Code and using local AIs and then uploading it as notebooks later on?
For
So I
AI
use
assistance, I
I
need to
use
double check with the
I use
coordinator.
VS Code and I use continue.dev and I use the Jupyter Notebook extensions for VS Code.
Yeah.
And then I tend to upload those to Colab after having developed it locally.
Okay, if you prefer to develop those notebook in your local machine, feel free to do that. Just make sure the version number for those frameworks is compatible with
Thank you.
the
Yeah,
Google
as a
Colab
legacy
version.
program, I'm more used to developing it in IDEs than in a notebook.
Yeah, fair enough. Because sometimes, because the local machine sometimes don't have GPU, like some students don't have GPU with their laptops. Maybe using the Google Colab will be helpful, and you don't need to go through the sophisticated local development environment settings. So yeah, but if you prefer your local IDEs, feel free to do that.
Thank you.
And
And
on
the
Friday, the
assignment,
labs at 9 o'clock, is that basically going through the labs that's posted up or new material?
You mean for the student consultation after 9 on
No,
Friday?
sorry, 9 o'clock. I meant 7. Sorry, I reread it. So 7 o'clock on
Yeah,
Friday.
from 7 to 9, we will go through the lab materials. So we'll go through the contents in the lab notebook and nothing more than that. And after 9, that's the student consultation time. So if you have any other questions, you can come to ask, but no new information will be
Okay.
delivered during that time.
Thank you.
yeah, the assignment one, submission of the code is on the PDF. No, it is not the notebook.
Yeah, the code is the notebook, and the report should be in PDF.
Code is not just copy and paste onto the
No,
PDF.
copy and paste. The code, if you download the Google Colab notebook, it will be a notebook file with .ipynb extension. I believe so, and then the report, you can use any editor, maybe Microsoft Word or something else, and then convert it to PDF for submission.
Right. Okay. The code should be in a notebook, no? Code should be in Colab. Okay.
May I ask, where is the notebook located in LMS?
Okay. Let me. Can you see the LMS page?
In the live sessions.
Yeah, go to the module and go to the live sessions, and all the contents are here, like lecture notes and the lab notebook, this IPy-NB. You can just download this notebook to your local computer and then upload it to the Google Colab space.
Okay.
So for each week's contents, just go to the module and go to the lab sessions. The lecture slides are there, and the lab notebooks and data are all there. And for the live recording, I think I would upload it to the same link as this Zoom link. Maybe I will place it at the end of this page, the live sessions page. Is that all right?
Yeah,
Yep. Just a question on our side. Where you just were in that live sessions section, under the section that says lectures, we've actually got a link. Well, I've got a link that says main notes, and it's like a 250-page PDF document from Andrew N. and I think someone else. Are we expected to know that, or is that just additional learning for our sake? Like, because it's
just supplementary materials for you.
Supplementary. Yeah. Okay.
Yeah.
Sorry, can you tell me again where the notebook? Can you tell me the link?
Sorry, what's the question?
The Colab notebook. You showed me it's in the lives, but I can't see it in the live session.
That's in each individual module's live session.
Live session.
Go
Module
to
one. Yeah.
let's say for this week, go to module 1 here. Go to module 1.
Yeah.
And then scroll down. There's a live session link.
Right. Live session.
Yeah, and then inside this live session
Okay.
links.
Okay, thank you.
No worries. Okay. All good?
One more question. With tonight's class, are we in a position to start on the finish assessment 1, or do we have to wait for material from week 2?
I would recommend you preview the lab contents from week 2 and start to work on the assignment 1 as early as possible. Because you can reuse the code in week 1 and week 2 lab materials. It will be helpful for you to prepare your
because I'm looking at the
assignment 1.
question there, and it's like, okay, I don't really understand. So I have to actually work with week 2 material.
Yeah, I think after Friday sessions, you can at least finish half. I think for task 1 is all right. You can use the week 1 contents.
Okay.
If you wait till the end of week 2 lab, I believe that would be a little bit late because we finished the Friday session, and then on Sunday the assignment is due. I'm not sure if you can finish that in 2 days.
That task 2 will require week 2 material, is what you're saying.
Yes.
Yep. Thank you.
Sorry, just quick follow-up. I didn't quite catch your comment on the main notes PDF. Could you repeat that, please?
Sorry, I didn't hear that clearly.
Sorry, can you hear me now clearly?
Yeah, a little bit better. So what's the question?
So you made a comment about this main notes.pdf. I didn't quite catch that. Could you repeat it, please?
So that's just supplementary materials. So if you want to know more about the know more about this each individual models, like their definitions and the formulas, you can have you can read it. So, but for the final exam or assessment, if you follow the lecture and lab contents, that would be enough. So this is just supplementary materials for you if you're interested to like learn more about it, learn more details about it.
Right. Thank you. Thank you very much.
No worries.
So I just have one more question because my background isn't in coding. I can see in the lab tab, I think the very last PDF, it says lab 1 script, and it shows you all of the Python functions. Is that all we need to know? So if we click on
It
that
shows,
final, yeah.
yeah, it shows you some common usage. Let's for like some common usage and syntax for using the Python. These are not going to be tested in final exam or whatever. Because this is not a coding course. But when you prepare your assignment, you need to use them somewhere. So yeah, in final exam, there will be no coding questions, no coding questions at all. But for the assignment 1 and 2, you need to do certain amount of coding part, although you can borrow like most of the code from the lab exercise.
Yeah, well, so is for assignment 1 and 2, is everything that we need to know for these codes, are they all on this list here?
For this specific lab 1 script, that's the basic usage, and I would say you let me hide it. I would say it will be more helpful for you to preview the second week lab contents. Let's say like you better preview the regression and classification notebooks, and also the data loading and pre-processing. It will tell you how to prepare the data, something like that. So I would say for assignment 1, week 2 contents will be more useful. Okay, any other questions?
Sorry, doctor, for the assessment, isn't required like to use the torch function, like to resolve this one?
Sorry, I didn't get it. For assessment, what's the
Is
question?
it required like to use torch?
Request to use what?
Torch to like find the tensor.
PyTorch. He's referring PyTorch, but we use the
PyTorch, yeah.
Oh, okay.
we use TensorFlow, isn't
it? You better use TensorFlow because I can double check with the coordinator, but I think you better use the TensorFlow because the marking that will make the marking schemes consistent for that.
Yep.
Okay. If no more questions, I will see you all on Friday's session.
Thank you, Dr. Zen.
Thank
Okay.
you very much.
Thank you.
Thank you.
Thank you
Have a
very
good night.
much.
Have a good night. Thank you.
Thank
Good night.
you.
Thank you. Good night.
Yeah, thanks.
Thank you. Yes, thank you.